it's been more than a year since I've participated in a conference, and I'm really excited about it. So without further ado, this is what we are going to talk about today. So Scala is not a very opinionated language, and it's a really expressive language, allowing us to express the abstractions that we need in our code. But we sometimes have overlapping solutions to problems. It's definitely not there's only one way to do it language, and that's fine. I love it for it. But sometimes for beginners, it can be difficult to make choices about which solutions to pick for problems. And one topic that often comes up is what to pick for expressing abstractions, a classic OOP-based design or ad hoc polymorphism via type classes. And we are going to talk about this choice for today. And as an agenda, and I have a lot of material to cover on some of the slides, I'm going to go a little too fast. So in case I end up without enough time, please see me afterwards in the Q&A session. We are going to talk about abstraction, what is OOP, what are type classes, the ideological clash between them, and conversions, how to convert from a classic OOP design to type classes and vice versa, and some recipes and best practices. Not as many as I'd like to cover. Hopefully we'll continue doing that elsewhere. So abstraction, and it's important to talk about it. Thinking about things like object types, we can find common traits between them, common traits that we like to focus on, for example, that solve our problems. If we look, for example, at these types in the Scala standard library, the top types are collections. 3 of these types can be iterated over and have an insertion order. Sorted set doesn't have an insertion order, it's sorted. This can be concatenated, but only sorted set has a concatenation that is commutative. A string also can be concatenated and is not commutative, it's just associative. Long has a commutative plus. These types at the bottom have what is called an error context with which you can handle errors. Option can also be used to signal errors that you don't care about, but isn't exactly like this. All of this can be iterated over. Array and vector can be indexed efficiently. Sorted set actually can be indexed fairly efficiently, but list cannot be. So as you can see, we can find common traits and similarities between them. We can group them, and that's the important part. And we can maybe focus just on those attributes that we care about for solving a certain problem. So abstraction, let's try to give a definition like in all good presentations. So to draw away, withdraw, remove, and this would be like the Latin origin, I think. To consider as a general object or idea without regard to matter, a member of an idealized subgroup, and contemplate it according to the abstracted quality which defines the subgroup. Or in the case of software development, we basically speak about idealization. I'm probably butchering the English language right now, sorry. Which means removing details that aren't relevant, you know, out of sight, out of mind. We only focus on what's important. And generalization, which means grouping object types in subgroups such that we can transfer knowledge, recipes, proofs. And this really translates into code reuse and correctness, which we'll talk about. And you know, we want abstraction in our language and in our programs, because managing complexity is like a juggling act. There is only so much we can keep in our heads, and removing details we don't care about is one way of managing abstraction. Code reuse is another, and so on. and our software projects only become more complex. And one important notion that we should talk about is the notion of the black box abstraction. A black box is a system, a program that is described only in terms of its inputs and its outputs. We don't care about what's underneath. What we care about is for the inputs and the outputs to be defined well enough such that we can form a useful mental model that allows us to operate it without breaking it. For example, of course, a function can be a black box, and are used for black boxes, but a more complicated example would be an automobile, which has a steering wheel, a gas pedal, and a brake pedal. And you only need to operate those in order to get a car from A to B without caring whether it's a diesel engine under the hood or an electric car. And cars are complicated beasts. Web service is another black box, right? And operating a web service is nothing like calling a function. It's more like operating an automobile. And if you want to hear about this distinction between useful mental models and reality, you should check out that book I recommend over there, The Design of Everyday Things, which I recommend to every software developer. Now, the purpose of building black boxes is that you can, connect multiple black boxes into bigger black boxes. And that is how we manage complexity. We create bigger and bigger black boxes that have hopefully clearly defined inputs and outputs. Now, no paradigm has like a sort of monopoly on composition, but FP developers surely like to talk about it. And when they mean composition, they speak about this. If you've got two functions f and g, if the output of f matches the input of g, then you can combine them together easily, like automatically even. Now, of course, if the output of f is something more complicated, like an I/O result, we start talking about other protocols for composition, like applicative or monads, and the good stuff. And this is basically what people mean about composition. You have clearly defined protocols for combining boxes together. Now, in terms of which is better for what, OOP is best for describing black boxes. And by the way, best doesn't mean that in an FP language like Haskell, you don't get facilities for describing black boxes. You do, and a language like Haskell is good for describing black boxes, but we are talking about what's at hand and what's common in that language's culture. So in OOP languages, people describe black boxes a lot because it's easy to do so. OOP is a great paradigm for doing that. And static FP is best for composing white boxes and black boxes alike, but there's a preference for white boxes. And by the way, in this talk, I'm talking about static FP. I'm not talking about FPS practice in dynamic languages, and there's a big difference there. So what is OOP? And I'm asking this question because it's a confusing question, and I'm surprised that if you ask 10 people, they might give 10 different answers. So of course, it's about relationships between objects that send messages to each other, but the defining properties of OOP, and there's only one defining property of OOP that personally I care about, is subtype polymorphism via single dynamic dispatch. Things get more complicated when we talk about multi-dispatch or row polymorphism, but OOP for me is subtype polymorphism, and encapsulation and inheritance kind of flows from that. Subtype polymorphism is basically the Liskov substitution principle, meaning that in case you have a piece of logic that requires, for example, a set, a supertype, you can take an object of a subtype, and that subtype can perfectly substitute for the supertype, meaning that a sorted set will behave exactly like a set in contexts where you require just a set. In practical terms, this means hiding information at compile time. You don't care about the sorted set being sorted, you just care about the properties of a set. This is idealization. We remove the details we don't care about. Are object-oriented programming and FP orthogonal? Well, yes, but with caveats. of course, when people ask this question, we think of immutable classes, but these are totally uninteresting because these are just record types. And by the way, if you inherit some traits for this customer here, you basically tell to the world that these getters and maybe setters these getters are meant for side effects. There are really few instances in which you need to inherit from traits in such samples from open traits. I'm not talking about sealed traits or anything like that. Those are algebraic data types. But the interesting classes are the ones that have state in them. So like iterator here, which basically mutates a reference, an internal reference, in order to iterate over a collection, and it has this great quality that it works for every collection type in Scala or in Java. And we can certainly turn that into something pure by simply suspending side effects in I/O, making the calls to those methods to be referentially transparent. And now we are FP compatible, let's say. Now, Martin Nedelcu loves saying that FP removes one important dimension of complexity. To understand the program part, you need to no longer account for the possible executions that can lead to that program part, meaning that objects with identity, in order to reason about them, you have to know their history of interactions to understand what will happen at the next call, at the next method call, what's going to be the result of that. And that is true, but he's basically speaking about idealized FP, because in practice, we also suspend defects in I/O. We still need to manage side effects. We still need to mutate shared memory. We just delay that until the edge of the program, so to speak. But this difference, for our purposes here, like, do you depend on the history of evaluation or not in order to understand what that thing will return, will evaluate to? That's basically a technicality. And it's not even about the classes. You can have this in Haskell too, right? Except that now the internals are all exposed and you can manipulate them without going through a well-defined protocol. Now that we've settled that, let's talk about type classes. But first, we are going to talk about parametric polymorphism. This identity function here is generic. It can take any type, and it will return that type. And if you look closely at its definition, this function can have exactly one implementation because we don't know anything about the A type parameter here. Of course, on top of the JVM, we can do hash code equals and to string, but we are going to ignore that because we are, FP developers. So parametric polymorphism in this case gives us clarity into what this function does. The more generic a function is, the less its implementation can do. For example, this foo function here can do a lot of things, like it can concatenate the input with something else, it can reverse the string, it can return an empty string, and so on. It has multiple implementations here. So take away this notion, an abstract function, a generic function, the more generic it is, the less it can do. Now, let's describe a function that lists a list of A's, and that is generic, that can work for integers and strings, and that also works for empty lists. This would be like a classic problem. We could first try to define that with an OOP interface. Assuming that we control the implementations of string and int, of course, we could maybe send a PR to Oracle. But would this work? Well, not really, because then we would be able to add strings with ints. And I mean, what is this? JavaScript? This is a fail, and Liskov is sad. Not going to work out because ignoring details is not good in this case. We obviously can't add strings to ints. And we can also use one Scala feature called the self type, which lets us work around that sort of, even though it complicates, the typing. But there's still another problem remaining, which is that we need an empty string or zero for ints. We need to start from somewhere, and that's not an instance method. That's a property of the class of the type itself. So, this too fails. And at this point, a well-grown Java developer would start defining dictionaries for the types, which are essentially type classes. We can define a combinable that has our sum operation, which we'll call combine, and then an empty function, which will give us like 0 or the empty string. And that will allow us to sum up lists of any elements whatsoever. And by the way, the shape of combinable kind of resembles the shape of fold left, of its parameters. Fold left is a little more flexible, but that's not a coincidence. So here we are passing this dictionary explicitly, which is what you do if you weren't in Scala. But in Scala, we can define that as an implicit instance, as an implicit monoid instance on integers, which knows how to sum up the numbers. And it's going to be visible globally. And this points to what type classes are. So type classes are basically dictionaries of methods and functions related to a type, not to an object instance, but to types, and that are globally visible. So the language provides us with a facility for discovering these instances at compile time. So that's what implicits are. This allows us to use these monoids in our code. I'm going to use the mathematical name here because you can search it up on Google and then see its properties. Combinable doesn't tell me anything. So that combine operation is associative, and the empty element along combined with another element is going to be an OOP. It's not going to have any effects, so to speak. So we can now define our sum in terms of this monoid. And Scala also provides us with some syntactic sugar here for adding a restriction to A. So type classes added to a type parameter are called restrictions. This sum is restricted now by monoids. And by looking at the signature, the parametricity holds. So we can look at this signature and infer what it does. What can you do with a monoid and applied on a list? Sum those numbers up, of course. So with parametric polymorphism, types dictate the implementation. It restricts the implementation. This intuition that the signature describes precisely what the implementation does is what static FP developers call parametricity. If you ever hear this violates parametricity in a PR, that's like an OOP developer saying program to an interface, not to an implementation, the ultimate screw you. So let's talk about the ideological clash between them, because there is one. This computer science is not evolved as a science. It's not using the scientific method. So we are talking about ideologies because human interaction is involved, social interactions, collaboration, and that stuff is hard to measure. So whatever succeeds in the marketplace, that's based on how fit the products and the tools and the ideas are for the current context we are in, which is an industry which is in hypergrowth phase. So popularity is an awful metric, but it's the best we've got, unfortunately. And this is why these are ideologies, because they have ideas about how it's best to do things and social movements behind them. So we should talk about what OOP values, and both want the same thing, except they approach it from different directions. Object-oriented design values flexibility of the implementation, backwards compatibility, black boxes, resource management. Now, in terms of resource management, FP got some sleeves up, has some aces up its sleeve. Sorry. But OOP is best for resource management, and resources also means memory management. I mean, have you ever taken a look at how a hash map implementation looks? OOP values backwards compatibility and flexibility of implementation, meaning that OOP interfaces promise less than the consumers of those APIs may need. But that's considered, let's say, sort of a good thing for the stability of the API, because updating APIs for the purposes of correctness creates friction in collaboration between teams and so on. And FP values like the reverse of that, static FP. Flexibility of the core site, correctness. I mean, if you ever find an API that's not correct because you've made a mistake, of course, you're going to break everybody's code. Dump data structures, and dump data structures are reusable data structures. Dealing with data, FP is great for dealing with data, and composition. FP talks a lot about protocols for composition. So you can view this as opposite sides, you know, kind of like left versus right, or progressives versus conservatives. One values correctness, flexibility, and flexibility of the core site. The other values API stability and flexibility of implementation. And of course, this is like a spectrum, because you know, I mean, it's useful to talk about the degenerate cases. The degenerate case for OOP would be an actor that is untyped. And the degenerate case for FP would be the identity function. Actors are degenerate because it can literally do anything. That actor here could literally send shuttles to the moon, for all I know. This is basically word of mouth typing. Whereas identity does literally nothing, being useful only for type Tetris and in presentations for proving a point. So I named these degenerate cases thinking about the degenerate era of the universe, where like stars are dying, turned into white dwarfs and brown dwarfs in their march to be eaten by black holes, because that's how I feel when I work with untyped actors, or when playing a lot of type Tetris. So, am I going too fast? Type class superpowers. We can extend types we don't control. And this is really important, because we can, for example, define an ordering instance for our own types, or for types in third-party libraries. Ordering being a type class provided by the standard library, which is super useful. But we can also do automatic instance derivation if we have an ordering for an A defined, or an ordering for an A1 and an A2 defined. We can define an ordering for the tuple automatically derived, or we can automatically derive an ordering for a list. And this is great. And this basically work like mathematical proofs. Static FP is a lot about mathematics. So here we can say implicit order for a tuple. If, in case we have ordering A and ordering B, we can define an ordering for the tuple of A and B. In case we have an ordering for an A, we can define an ordering for a list of A. Now the implementation is not really important here. I basically, I might find a more elegant implementation, but I did this half an hour before the presentation. And you can derive pretty much anything, including case classes, but for case classes, you have to use shapeless, or maybe, what was that other library name, Magnolia? But those are, you know, based on macros. So if you want to have some fun and crash your compiler, you should try one of those libraries out. In general, I stay away from deriving instances for case classes, but if you want to do that, there are possibilities, like, I don't know, if you want to like write another JSON library. So, converting between styles. We are going to start with a nice, clean OOP interface for JSON serialization. Of course, not even Java developers do this. Java developers do things at runtime. So in order to turn an OOP style interface into a type class, you basically add a type parameter, and every function that used to operate on the object instance now needs to take an explicit parameter. And this would be like a good type class definition, a nice and simple one that's actually very usable in practice. And JSON serialization is a great use case for type classes. Now, of course, the more interesting examples are the OOP classes that have state. And here we have to apply some functional programming. Because the state needs to be exposed. And here I'm using an abstract type member to expose a cursor in this iterator that will basically be mutated along the way. But here we are using a pure definition of next. So we are returning the next element and the next state. This will be, if you search on Google, the state monad. I mean, the shape of this signature, what's important here is that we are working with immutable data structures, and we may not want that for performance reasons. Sometimes, I mean, this goes back to what Martin Nedelcu is used to saying, that we can evaluate a function without knowing its history, but sometimes for performance, it's better to like do side effects and maybe suspend those in IO. So an alternative definition would be one that uses IO for the side effects. In this case, cursor can be something side effecting. So for a list, we could use like, actually we could shove the real iterator here right now. Yeah. So, and this definition would be perfectly equivalent to this OOP class that, you know, suspends side effects in IO, but you can see the difference here. In the case of OOP classes, the state is implicit, it's being held by this, and for type classes, the state is explicit, being taken as a parameter. So everything becomes a parameter. Type classes expose functions. Some things to keep in mind. So sometimes type classes expose its internals wide open, and you may not want that. And also type classes introduce the need to have hierarchy types. As soon as you have type classes in the language, you also start needing to talk about types that have type parameters. That's what a hierarchy type is for. So, and you know, this kind of introduces, you know, the need for extra expressivity, extra, you know, features in the language. Haskell is a more expressive language than Scala, for example, and in Haskell, it's better to talk about hierarchy types than in Scala. So in Scala, we need good taste for when to use type classes and hierarchy types. Let's go in the other direction, converting type classes into OOP. With our favorite type class, the monad, and we are going to split this one in two operations because, of course, the monad cannot be converted because we've got a data constructor in pure, and we've already seen that in what the monoid instance. So OOP classes cannot express data constructors or anything that doesn't you know, depend on that object instance. So we may be able to turn the flat map, but this one is difficult too, as we've seen with the monoid combined. This would be like a first attempt from an OOP developer. So, you know, we've got a function that takes a function returning flat map and it returns flat map. But we can't compose monadic types like this. Things would have been much simpler if we could, but we can't. So this is another fail of the Liskov substitution principle. We don't need that here. We actually care about the types. So we can use another facility provided by Scala and not by other OOP languages. We can specify a self type here with a recursive type parameter here to let the compiler know what it is. And this is called F-bounded polymorphism. And it's absolutely awful. So it's not useful for actual polymorphism. Its only usefulness is in sharing implementation details, and the Scala collection libraries are doing that. So don't do this in practice. It's absolutely awful. In case you need to express flat map, express it as a type class, right? Type classes to OP, not always possible. And this is why in OOP we talk about design patterns. A design pattern is usually a name for an abstraction that your programming language doesn't let you turn into a library. Yeah, in case you can't express something as a type or as a function or of sorts, that's a design pattern. And it's okay to talk about design patterns in object-oriented programming, but you know, things are less formalized. Recipes and best practices. I hope I have enough time, which is why I made an agenda, because I may not use my time wisely, and these aren't all the things I want to talk about, but at least I will be able to name them. So use type classes for data serialization. They are great for that. Whenever you have a data serialization need, just go with type classes. And like JSON serialization, although there are some caveats there, because you may want a different JSON serialization for depending on the use case. But you know, we can simply ignore the coherency rule or define the new type there. Use type classes for expressing data constructors. We've already seen monad and monoid, things that create objects, not use them. Use type classes for usability of dumb data structures. Type class instances must be coherent, globally unique. This is a best practice that cannot be enforced by the compiler. Of course, we can ignore that when we need, but it's best if we keep it as a best practice. Avoid orphaned type class instances, but do what you must. Type classes must not keep state. Use OOP for managing resources information hiding. And this one is going to be painful. Use principle of least powers default to object-oriented programming. Sorry. Use type classes for data serialization. This is like a quick example from our own code. We defined a type class that handles logging, and this is because we want our logging to not log sensitive data. So for example, we don't have an instance defined for strings or ints or big decimals, because we might log sensitive stuff. And we also have like a safe logger abstraction in our code base that uses this type class. And this log message is like a data structure that resembles YAML. I mean, it can express strings, maps, lists, you know, and it can build like a nice output whenever we log via logback. So in our own code base, we log via this safe interface, but well, we also have like other libraries. This is a league abstraction because other libraries will log with whatever they want. But in our own code base, everything is safe and nice, and this would be a great use case. And also JSON serialization libraries like Churche use type classes, and it has, of course, caveats, it has issues, but at least it's not Jackson. Use type classes for expressing data constructors, which we've already mentioned. Quick exercise. Let's do a function. Let's pretend that traverse doesn't exist and do a function like sequence that can transform a list of IOs into IO of lists. We can't do that with OOP with just an iterable, because we need a data constructor. We need to build a data structure, not just iterate over it. And in order to do that, we might come up with our own type class that's nice and efficient, that specifies a buffer that will collect elements. So for list, that's going to be the list buffer. For arrays, that's going to be the array buffer. You also specify a way to iterate over it, and we are going to use some OOP stuff here. A way to build the buffer, a way to append to the buffer, and a way to convert that buffer into our final collection. And that's all we need. And by the way, this type class is close to the build from Scala standard library, which they use in the standard collections for, you know, transforming collections. We can quickly define an instance for a list. So as I said, the buffer for our list is going to be the list buffer. These are, by the way, intermediate values. Abstract type members are good for specifying intermediate values that you don't care about after you're done. Sequence then becomes like a type Tetris with that type class. You basically iterate over it with a for, left, blah, blah, blah. The implementation doesn't matter. All that matters is the signature of sequence. And if you see that this is a collection builder, which means that you can build a collection and iterate over the old one, and then you see the signature here, it's pretty much clear what it does. So again, parametricity for the win. Use type classes for usability of dumb data structures. This is a trait that Haskell developers love to brag about. Here we have an example of a binary tree that's not necessarily a binary search tree. It's an awful example, by the way. And we can define functions that pretend that the binary tree is a binary search tree. So we can say it's a sorted set. And then we can have an inefficient set that doesn't take an ordering restriction and like treats that binary as a sort of very inefficient array or something. So we can have like this too. So we can clearly see the reusability here. It's an awful example, but it's the best one I could come up with for this presentation. And here we get to one common issue with type class design in common use in Scala. Type class instances must be coherent, which means globally unique. Because if we have the sorted set initialized from earlier, and by mistake we import another ordering instance in our scope, because we are importing with wildcard, we can break our sorted set. This is an issue of correctness. If type class instances aren't globally unique, we need to be really careful where we import those quote-unquote orphaned instances. Like here, maybe we know what we are doing, but we need to be really careful about these imports. So it's fine if we have exceptions, but remember that if type class instances are not globally unique, this is a correctness issue. Now, there's a caveat. Dumb data structures can be misleading. Some of them are not that dumb because sometimes invariants set by the use functions are too important. And again, this sorted set in the Haskell community is sort of like a bad example for dumb data structures, because this can happen. I mean, in case you build a sorted set and then try to use the functions on the inefficient set, that's just inefficient. But the other way around, it's a malfunction, because the sorted set is going to search via as if that binary tree is a binary search tree. And of course, it's not a binary search tree. This is a type safety issue. So the easiest thing to do is to add that restriction on the data structure itself. So now we say A must implement ordering. And when we see that, because parametricity, we can figure out that this is a binary search tree. I mean, what else are you going to use this ordering for? And this is actually saner, and it's what Scala standard library does. And it's why maybe in Scala we don't need global uniqueness that much, even if we have to keep it as a best practice. Now, type classes must not keep state, and this is a super important one. If it keeps state, if a type class instance keeps state, it's not a type class. So I'm going to give an example. This would be like an interface for a registration, the registration of users. So it's going to save in the database and it's going to send an email, let's say. It's not a type class, and you can see it from the signature. You can see that in order to save to a database and in order to send an email, you need a JDBC database connection and you need an SMTP email connection for sending emails, and you don't have these as parameters, so they need to come from somewhere, so it's shared state. And of course, everything is fine if we do this. I actually like this, but This is not a type class. This will have a constructor somewhere, like taking the user DB in the email service and then building a real registration service out of that. This is OOP-driven design. To turn that into a type class, we have to add the environment. The environment meaning the JDBC connection along with the SMTP connection for sending emails. That needs to be visible in the signature. So we could add another type parameter here, like an env, which is going to be a parameter of register user. And everything is going to be explicit. So I basically did a half-baked cake here in order to specify these dependencies here as the environment. And this instance here, you can clearly see it that it's going to be a user DB and an email service, and you can see again parametricity from the type that it's going to save a user and send an email. Well, there's always the question of, do you really need that? And then you can define like a fake registration service that instead of the environment, you have a unit or something fake like that, that doesn't do anything. And then you can see from the signature that it's a fake registration service. That's, you know, again, another problem. I feel like I'm going too fast here, sorry. Another problem is that we used two type parameters here, and, you know, type parameters in Scala, too many type parameters are not good for our health. And we can try to simplify that with a single type parameter by making it more complicated. And in order to do that, F, by the way, F in these samples can be IO. So it's basically like the type that is going to suspend our side effects. So that's why we need the environment and we need F. That can be IO or could be ID for the fake implementation. But here we get rid of F. I mean, we could put IO everywhere, but then IO can launch missiles to the moon. So we still want to work with F. So we put F, the type parameter, on the function itself. And then F is, the environment is going to be parameterized. I'm butchering the English language by F. So one interesting difference here is that we need this monad restriction here, and this is we really need it in order to combine the sending of an email with the saving in a database. And this adds a restriction on the possible implementations. For example, we couldn't do those things in parallel. For that, we need to add in the interface another type class like parallel. So it's going to show up here instead of showing up here in the instance implementation. And that can be okay, but you know, not really. I mean, sometimes it's best to just stick with OOP-driven design for managing resources and information hiding. I don't need to know that personally. I don't need to know that a registration service uses database and SMTP connection under the hood. I mean, take a look at this signature, which is like the OOP-driven design. For me, this is much simpler, even if some correctness is sacrificed. And let's also talk about what I said in the beginning. OOP hides implementation, preferring flexibility of implementation. Here we are not exposing an error type. Should we have exposed a JDBC exception? Maybe. I mean, that would have given more flexibility at the call side. The consumer would know better what to do. But that JDBC exception is an implementation detail, and it leaks implementation. And what happens when the implementer is going to change the implementation of this to use a Redis connection or something else? So that's what I meant by flexibility of implementation, the flexibility to change the engine under the hood without the user noticing via the type system. And of course, it can be said that not exposing the error type is an undescribed error condition, but sometimes that's okay in case we are talking about this distinction between input errors and faults. And here Liskov is happy. right? So here is one of those cases in which I think the risk of substitution principle perfectly applies. So one last final advice: use principle of least powers. You have a complexity budget. All abstraction has a cost in use, tooling, learning, curve, comprehension, and don't use the type classes if an OOP class or a higher order function would do. Scala is not Haskell. I mean, it's not as expressive as Haskell. All type classes need to be defended. All type parameters need to be defended. All abstractions need to be defended in PRs, right? And beware of false abstractions, meaning that if you don't have two samples that you abstract over, that's not an abstraction.